Good morning, my dear students. Welcome to this session on moment distribution method. The last session we have completed an example of two-span continuous beam with fixed ends. In this session, let us take a three-span continuous beam with fixed ends. Okay, so let us see the problem first. Analyze the continuous beam shown by moment distribution method and draw BMD. So we have to use moment distribution method for the given problem. So if you observe the diagram, there are three spans which are AB, BC and CD, where span AB is 6 meters with 1.5 times of I moment of inertia. With a point load of 60 kilonewtons eccentric, which is at 4 meters from left support. You have span BC of 3 meters and moment of inertia I, a load of UDL 20 kilonewton per meter. The whole span of BC is being loaded. Okay. Span CD is of 8-meter span and moment of inertia of 2I. It's a point load again, which is at the center of the span. So 4 meters from right end or else 4 meters from left end, whichever is. Both are same. Right. So once you recall the procedure of moment distribution method, so first we shall write fixed end moments, then we shall calculate distribution factors, then we have to complete the distribution process wherein distribution table we have to make, and you have to complete the distribution table, and finally you have to add all the moments at a particular end of a member so that you will get end moment values. This is the procedure. So we'll start with the first one. So for span AB, fixed end moments, you have to fix the span AB. Consider AB as fixed beam. I'm not going to draw it. So you have to understand, because the earlier session we have seen the problem with detailed explanation. So you just take this as a practice problem. So just follow the steps and try on your own. So span AB, we have eccentric point load where the bending moment at A, fixed end moment at A, MFAB will be left support will be having anti-clockwise moment. That's why it is minus here. You will see anti-clockwise moments are negative sign, given negative sign. So PAB square by L square. This is A and B is equal to the remaining span 2 meters. Okay. So P is 60 kilonewton to A 4 meters, B 2 square divided by L is 6 square. So that is coming around minus 26.667 kilonewton meter. Now the other end, MFBA is equal to, formula turns out to be PA square B by L square. Okay, which means 60 into what is A square? 4 square into what is B? 2 divided by L square, 6 square. Okay, so that comes to be 53.33 kilonewton meter positive. Okay, so left anti-clockwise, right clockwise direction of moments are developed at A and B if it is a fixed beam. Okay, right. Next, when you take up BC, it is a full UDL on BC. So moment at end B, moment at B, fixed end moment at B. MFBC is equal to, again, minus here, left anti-clockwise, WL square by 12 is the fixed end moment. So 20 into 3 square divided by 12, that is coming to be minus 15. Similarly, fixed end moment at C, positive, and the same formula because of symmetry. Fixed end moment at C also same, but with a different sign. So WL square by 12. Now, if you take portion CD of the continuous beam, if you treat it as fixed beam with central point load, so moment at C, fixed end moment at C is equal to, again, minus PL by 8 because of the load position. So P is 30, L is 8 divided by 8. So it is minus 30. Similarly, fixed end moment at D is of same value but of different nature. Reason because of symmetry. So 30. So these are the fixed end moment values. That means when you assume that each span is a fixed beam, AB is a fixed beam, BC is a fixed beam, CD is a fixed beam. Okay, right. So what is the next step? You have to calculate distribution factors. Okay, so what is the table that you have to get it right? So remember, joint, first joint, then the members, then the k value, which is 4 ei by L is the formula, and then joint stiffness, that is sigma k, and then distribution factor formula, k of a member divided by joint stiffness of that concerned joint. Okay, now if you see the diagram, given continuous beam, there are two joints, joint B and joint C. A is not a joint, D is not a joint. So joint B has got two members. BA, read the joint name first. BA, BC, two members. Similarly, joint C, two members. CB, CD. Okay. So likewise. So write the joint name first. Then member names. BA is a member. BC is a member. Similarly, joint name C, member names CB, CD. Okay, right. Now, stiffness values of all the members, all these four members, we shall calculate stiffness value. So, 4EI, what is I for BA? 1.5 times of I, okay, divided by L. What is AB span? 6 meters. So 6 meters is substituted. So that is 1 times EI. Okay. 1.5 into 4 is 6. 6 by 6 is 1. Okay. Right. BC 4EI, I is I for BC, by 3. So it is 1 point, L is 3 meters, so 1.33 times EI. Similarly, CB 4EI by L, same value. For CD, it is 4EI. I means 2I for CD. So 4EI by L is 8. So it is EI again. So what is sigma K? See, be careful with these, cells, how you make cells. That these two you have to combine, and these two you have to combine here. See, joint, it is related to joint. That's why you have to make by combining these two and make a single cell. Similarly, joint corresponding, you have to make a single cell here. But when you have a member, you have to have an individual cell here. So 4 rows will become 2 rows here. Again, distribution factor is for member. So you will have 4 rows again. Okay. So you have to make a table like this. So now for BA, what is distribution factor? K of BA, that is EI divided by sigma K of the joint where BA is there. What is a joint? It is B. So EI divided by 2.33 EI, and the value is 0.4. Got it? So EI divided by 2.33 times EI. So it is 1 by 2.33 value 0.43 is the distribution factor for BA. Similarly, BC 1.33 EI divided by 2.33 EI. Okay, and the value is 0.57. Now, while you rounded off the value, the total should be 1. Okay, right? So you cannot just round it off to any extent. You cannot make this as 0.43. Say for example, if that value is 0.432 or something, so we are taking it as 0.43. Now if it is other value is 0.5655, okay, you can't take this as 0.56 because total is not equal to 1. Okay, so you shall take this value as 0.57. Okay, so then only it is total is 1. So while you round off the value, you have to make sure that total is 1. Right, same here, 1.33 divided by 2.33 is 0.57, and 1 divided by 2.33 is 0.43. Okay, right, this is how we find distribution factor values. Okay, right, next going for distribution factor table, I mean distribution table. Okay, so how you follow the moment distribution procedure. Okay, so as I said, draw a line like this and write all these A, B, all the ends. What do you see in the given problem? Okay, right. So all other middle nodes or else middle ends, I mean to say middle points of the given beam shall be drawn with a vertical line at their center. Center of B you draw a vertical line, center of C you draw a vertical line, and then at the end, after the end point, you draw a line. Then before this starting point you draw a line, then you make a column there, make a column, okay, to notate the process that you are doing, okay. So to start with, what you do, first you make this as a row, right? All the nodes, end nodes of a continuous beam, okay, right? You have to make a row. Then write distribution factors what you have found. Sort of distribution factors. Giant B, BA is 0.43. Giant B, BA, okay, at B 0.43. Giant B, BC 0.57. Similarly, giant C, CB value. Giant C, CB value is 0.57 and again 0.43. So you can write just in order all four values. You don't have any distribution factor at A and D, okay? Remember. Next, what you write? Fixed end moments. Write all the fixed end moments found here in order. At A, what is a value? At B, what is a value? Okay, in AB, minus 26.67, 53.33. So under A, you write that value. Under B, you write this value. Again, BC has got two values, minus 15 plus 15. So minus 15 plus 15. And minus 30 plus 30. Okay. So it's minus 30 plus 30. Okay. So likewise, we write fixed end moments. Now what you do? Take first giant. Giant B. What is total moment there? 53.33 minus 15. 38.33 is the remaining value. That is a balance there. 38.33 is the balance. Okay. So what you should do, you have to make this as 0. To make that as 0, you have to add minus values. Okay. If the positive value is the balance, so we are going to add this minus value to the two members at that joint. How do you add or how do you share it? Minus 38.33 is just by multiplying with this distribution factors. That is how you distribute to two members. So minus 38.33 into 0.43 is this value. Minus 38.33 into 0.57 is this one. Okay, so if you add these two, you will get minus 38.33. Okay, so this is about balancing at giant B. Same here, take giant C, balance this value. What is the total value? Plus 15 minus 30 means what? Minus 15 is the balance value. So to make it 0, you are adding plus 15. So how do you distribute it? Plus 15 into 0.57, this value. Plus 15 into 0.43, this value. Okay. So this completes balancing activity. Balancing is completed. Okay, we have balanced the joints. Then what next? So once you add some moment or apply, adding means what? You are applying this value. Once you apply moment at one end, opposite ends, if it is fixed end, then half the moment will be carried there. That is what is called carryover moment. So balancing is over. Then we have to calculate what is a carryover moment. So this is the value applied. Then draw an arrow like this to the next row. Make a next row. So take half the value and write it here. Minus 16.48 by 2. Okay, this is carryover. Then joint, I mean to say the other end. Okay, joint B has got two far ends. Joint B has got two far ends. One is A fixed. C is also must be treated as fixed. Okay, why? Because that is a continuous support. Okay, so that is the reason you have to carry to the C also. Okay, so minus 21.85, half the value, right? So joint B carryover moments are done. Come to joint C. Joint C has got two far ends. One is B and another is D. So that also has to be carried to far ends. So for C, B is a far end and D is a far end. Okay. So this is far end for this and this is far end for this. So half of this value. Draw an arrow like this where you are carrying from C to B. So C to B, you are carrying half the value. Same here. From C to D, you are carrying half the value. Okay. So that completes carryover moments. Okay. Observe here. From B, we have carried forward the moments to far ends. For B, A is a far end, C is a far end. Okay. And here you are considering continuous support also as fixed end. Okay. So that's why half the value goes there. Now if you see, giant B is having some moment now. We have made it 0 earlier. Earlier we have made it 0. But now what happened? Because of balancing of C, some value is developing at B. Okay. So this is not 0 now. So again you have to make this as 0. What one? Which one? 4.28 is the balance value. Okay. So make it 0 means what? Minus 4.28 shall be added. How do you add? Again by multiplying with distribution factor 0.43 and 0.57. So these are the values. Same coming to C, we have made it 0 at joint C. Total moment at C we have made 0. But what is happening? Again there is a moment of minus 10.93. How this has come? Because of balancing of B. So you have to make this 0 again. So what do? You add plus 10.93. Add 10.93. How do you add again? 10.93 into 0.57. You write it here. 10.93 into 0.43. Write it here. Okay. So you have to distribute the two members joining at C. Again, you have applied some moment values at B. So you have to carry them to far ends. Repetition. So balancing is done. again you carry half the values. So when you carry half the values, again the joint is disturbed. 0 is disturbed and 0 is disturbed here. Again you make it 0 by adding the opposite value. If it is plus, you add opposite values. So minus values. If it is minus, you add plus values, opposite values. How do you add? By multiplying with the distribution factors and carry. So likewise, balancing carryover, balancing carryover, and finally balancing. We will balance and stop. Okay, because you see, giant C is having almost zero. Is the balance value 0.057 and here is 0.1. So I'm going to stop with this accuracy. Okay, I feel that when compared to 53 kilonewton meter, zero point 0.1 kilonewton meter error is okay for me. Okay, that's why I stop here. Now what I'll do, I will add all these values and write it here. This is MAB value. This is MAB value. Okay, this is MAB. I'll add these values. If they are minus, you have to deduct from this. Don't try to add this one. This is different. This is distribution factor. Okay, so you will get 33.4. Same here, you add from minus 15 all these values. Okay, according to their sign. So you shall get exactly opposite sign with same value. Same here, add all these values, get this. Add all these values and get this end moment. Add all these values, get the end moment. So this is MAB, MBA, MBC, MCB, MCD and MDC values. Okay, this completes the moment distribution process. Okay, right. Now, how you draw BMD is again same, overlapping the negative moments or support moments, and then finally overlapping them by span moments. Okay. So if it is, if you see minus 36.6 is the moment at A, so this one 36.6 minus means anti-clockwise, and B, if you see 33.4 positive means clockwise, 33.4, and again it is minus 33.4, and this one MCB plus 17.9, this is 17.9 minus 17.9, and finally plus 36. So plus 36. So take AB, 36.6 negative moment, 33.4 negative moment, means hogging. Just join those two end moments. This is end moment diagram. Then span moment diagram as usual. Take simply supported beam, calculate PAB by L. You will get bending moment under point load is maximum. Draw a triangle, because simply supported beam with point load bending moment diagram is triangle. Again come to BC, again same value 33.4, then 17.9, join those two and draw BMD for UDL, WL square by 8, that is a parabola. Okay, and that value shall be almost very less in value. I'll just tell you the value. It is W20 into L square 3 square divided by 8 22.5. So this maximum value is 22.5 kilonewton meter. Okay. Similarly, CD, if you take, this is same 17.9, then 36 again. So join those two, we'll get negative moment diagram. Then this is WL by 4 or PL by 4 is the maximum bending moment. If the point load is at center, PL by 4, so that is 60. Draw a triangle. Now this is a negative moment, positive moment, negative moment. This is all negative because positive is very less value. So negative, positive, and negative moment. Okay. So this is how we complete BMD. It's very simple. First draw end moments or support moments, then overlap the span moments, which are simply supported beam with the given loads. Okay. So this is how we are able to complete the example problem of three span continuous beam with fixed ends. Okay, right? So try solve this example, which is of October 18. Using moment distribution method, analyze two span continuous beam. The moment of inertia of AB is I, whereas BC moment of inertia is 2I, and A and C are fixed. And sketch bending moment shear force diagrams. Span AB concentrated load 40 kilonewton. Concentric means at center. The span 8 meters and span BC carries 30 kilonewton per meter. Span of BC 10 meters. Solve this one, which is very similar to the first example that we have been solving for this case. Okay, this is the example that we have solved. Okay, the same procedure you follow for this university question, JNTUK university question. Okay, right. Thank you. We'll come back to the next session to discuss about what happens or what is the change in procedure if continuous beam is having simple ends, means hinge or roller at the end. Okay, we have solved till now fixed ends. Now if the end is also a hinge or roller, what is the change in procedure? Okay, thank you.